This is fabrication technology, and the biggest problem with doing this is you end up getting a 25-minute lecture, and the students in years past have said, well, it's too small a lecture to really kind of get into things, so you just have to live with it. If you don't like it, watch the video and put two of them together or something. But it's it is kind of a catch-all. It's not just for naval constructors. It's kind of adds some topics to joining in fabrication. I won't be talking about, it's primary structural materials, I guess is one way to put it. And in fact, the first thing I've done is put up something here from Ashby's book, and this is in your bibliography and stuff. In fact, there's a handout in there from this. Material selection and mechanical design. Mike Ashby is retiring from Cambridge University, but he was a professor up at Harvard early in his career, and he's one of the great material scientists of the last 50 years, so far as that goes. But he is a structural materials person, and he has the ability to look at things in a very broad, general way, and put things together in more of an integrated fashion than most other academics. This is from that book, and it talks about the relative importance versus time of different classes of materials. It's not a very linear scale down here. I got this focus. It's sort of hard. In any case, there is a hard copy in your handouts. It goes from 10,000 BC to 5,000 BC to 0, and then to 1,000, and then you're getting in 1940, 1960. Like I say, it's sort of expanded out on this side. But he points out that originally we had metals, which were only gold. Why was it only gold in the beginning?
Soft.
It's soft, but it's also one of the only elements that's found in its metallic state in nature. I mean, you can find gold nuggets, and you can hammer them out. Turns out in some parts of the world, such as Michigan, you can actually find copper nuggets, and I've seen native copper nuggets that are, weigh half a ton or so. But until people learned to smelt metals, you didn't have metals as much. You had polymers and elastomers, except those were wood, skins, and fibers. You had composites, which is straw, brick, and paper. And you had ceramics and glasses, which is stone, flint, pottery, glass, and things. And then, of course, these are kind of simple things. You saw a rise of metals up through the 1960s, and then he says in the 1980s the use of metals tended to drop off. I'm not sure that I necessarily agree with all that, and we'll talk about it. But does anybody know why, if I turn this over, why the use of metals rose so dramatically as a structural material over the ages? We started using less stone and concrete and stuff.
It's strong. It's easier to put into shape.
It's formable. It's kind of hard to form concrete. You try to form concrete and you get powder, right? Yeah. It is strong. It's incredibly strong. Its strength to weight ratio is actually very, very good compared to all these ceramic materials, so far as that goes. It's also very ductile, which means it has good fracture resistance. The Achilles heel of metals, though, is in nature they want to go back to being an oxide or a sulfide, and so they corrode. And so we're always fighting corrosion problems in metals, but in terms of their inherent strength and ductility and toughness, they're unsurpassed. Now, people will tell you about fancy composites and stuff, and I'll do it in the next class on some of these things too, but this is a piece of the skin of the X-33 spaceplane hydrogen tank, which failed about almost 2 years ago. This was going to replace the space shuttle of this spaceplane, the X-33, was the prototype that was going to be the next generation development vehicle for the next generation space shuttle. And this consisted of a epoxy resin and graphite fibers there are 13 layers in the thinner section here of graphite fibers that have tremendous strength. I mean, when I was looking at one of these things down in Huntsville, I basically just touched it. One of the fibers got stuck in my finger for, just for a couple of weeks until I finally, as a splinter, I finally got it out. But just very, very stiff, very, very strong. You lay it together with some plastic, and then you have this called Hexel core, which is a honeycomb core, like a beehive. It's basically made out of Nomex or Kevlar, very strong polymer. Okay, and then originally this had another layer inside. Actually, this is only 7 layers, and the inside layer was 13. It's got a doubler on here. The tank, roughly twice the size of this room. Okay, there were 2 of them, and they only weighed 5,000 pounds. How much do you think they each cost?
How much do tanks cost?
A tank? It's just going to hold liquid hydrogen, right?
Yeah.
In a space plane, right? They cost $50 million a piece. On a per pound basis, that's $10,000 a pound fabricated. Okay, if I go back to the numbers I had up there before, the cost of materials for a typical structure is 10 to 20% of the cost. Well, you go to a fancy composite like this, and you might get down to the material cost may only be 2 or 3%. Still pretty high. But let's go and think about a ship. Okay? You make a ship out of steel. Let's say I'm making a commercial ship. So what's that steel cost? Anybody have an idea? If I go to the store and buy a plate of steel?
$5 a pound or
No, it's 50 cents a ton.
50 cents?
Okay, $1,000 a ton for a good quality plate. That's actually pricey. You can probably get it for 40 cents a pound. Okay, and if the cost of the structure is roughly 10 times that, that's $4 a pound fabricated. Well, I mean, another way to think of it is, what's a Ford Taurus weigh? About 4,000 pounds, roughly, right? What do you pay for a Ford Taurus? $20,000, $15,000, depends on how many options, electronic options you get. But let's say it's $15,000. Okay, that's $4 a pound fabricated, right? That sheet steel is worth about 25 cents a pound, maybe 30 cents a pound. So you got that roughly factor of 10 between buying the material and fabricating and selling the product. There's lots of things that go into that. I mean, Lee Iacocca used to point out that $3,000 of every Chrysler car was health insurance for the workers. Okay, he was just complaining about health insurance costs. But no matter what it is, the material costs are a relatively small fraction. So let's say I'm going to make a nuclear submarine and I'm going to use HY80. Anybody know what HY80 costs per pound from the mill? Instead of 50 cents a pound or 40 cents a pound for the plate, HY80 has got 2.5 times, or HY100 has 2.5 times the strength. So you think the steel mill is going to sell it for less than 2.5 times as much, right? So 2.5 times 40 cents is $1. Well, it turns out HY80 is about $2 a pound. So what do you think it costs to fabricate HY80? $20 a pound. I mean, just order of magnitude, it's not hard to come up with these numbers. People wanted to build titanium submarines. Titanium, you're going to make for the submarine anywhere from 25 to 30 bucks a pound. So what's it going to cost to fabricate it? 300 bucks a pound. Okay, to buy the hull. So now you can start saying, well, why don't I build titanium submarines? Well, if you want to pay 300 bucks a pound for a submarine, you can. Okay? There are actually other reasons. Anybody know why the Alpha is not going anymore? Stress cracks, right? And actually, there's if you don't know what the Alpha is, if you haven't read Tom Clancy and The Hunt for Red October or seen the movie, the Alpha is the titanium submarine the Soviets built around 1980. And in fact, if you want to see an electroslag weld in titanium, this one was not made here, but in fact, the first electroslag weld in titanium made in this country was made about 1980 in my lab downstairs. This was made at Oregon Geriatric Center a couple years later because they started to classify this stuff. And MIT doesn't do classified work. But that's the weld. This is just a section from the weld. It's a 2-inch thick plate. And they got little dotted lines. The weld is this whole thing right here, titanium. Okay.
So is titanium more brittle, less ductile?
It's less ductile. It's less ductile. It does not have the fracture properties, but the Navy Research Lab in 1980s and even in the late 70s knew there's something called a creep fatigue interaction. You talk about stress cracks. Well, it really is probably, I don't know, it's stress corrosion cracking. Titanium is pretty resistant to stress corrosion cracking, but there's a creep fatigue interaction. If you stress it and maintain the stress, and then unstress it, there's kind of a synergistic thing, and the cracks grow much faster if you stress it, maintain the stress, and then release the stress. Well, what do you do when you go in a submarine? You stress it, maintain the stress while you're in, you'll come back up. And so, creep fatigue interaction. The U.S. Navy knew about it. Naval Research Lab was studying it, and they were very concerned about doing it. And then the Soviets came out with the Alpha sub, and we got to catch up with them. The Alpha sub would go 40 knots underwater, faster than the destroyers on top of the water. Could dive deeper than the collapse depth of our depth charges. Although one friend from out in Colorado said, well, depends on what kind of depth charge you hit it with. If you hit it with the right type of depth charge, you only got to hit it within a couple of miles. However, if you start using those types of depth charges, then you got a bigger problem. In any case, people were very, very concerned for a few years until the Alpha sub started being dry docked. Okay, they were also as noisy as could be. Okay, it wasn't hard to track. Okay, you knew exactly where they were, and that's also not something so good for a submarine. In any case, titanium is very, very expensive to fabricate. What could be a hull in a SSN-21 that the hull is worth $500 million. I mean, I know the SSN-21 is about $2 billion, but that's when you put all the electronics and the warheads and everything else in it. The basic hull, mechanical and electrical, is maybe $500 million. But if you were to jump from $20 a pound to $300 a pound, yeah, you get a savings in the lightweight of titanium. So on a per pound for equal size ship, maybe you're only paying $180 a pound, but still going from $20 a pound to $180 a pound 9 times, you're talking a $4.5 billion hull before you put the other stuff in it. And it wasn't clear that Congress was going to be willing to pay for that, particularly after you were basically playing catch up with the Soviets. So that was part of the problems in the early 80s until the Soviets had to dock it. But there were some workshops. I went to a couple of workshops where they were going to leapfrog Navy technology, or the Soviet technology, and they're going to make composite submarines. Okay? Well, I just passed around a little composite at $10,000 a pound, fabricated. So now you want to start, it's lighter weight submarine, you can dive deeper, but and on an equivalent basis, you're still talking about something that probably cost you $2,000 or $3,000 an equivalent ton for a same size vessel as if it was in steel at $20. So you're talking a factor of 100 roughly increase in price. So, but nonetheless, they spent $100 million looking at the potential building composite submarines. Some of us knew it was a waste of money, but you couldn't tell the technologists, the people who were pseudo-technologists out there, that they had some major problems. Was
the price the showstopper on that?
Well, it wasn't the only showstopper. Another showstopper on composites is you can't repair them. In fact, I remember at the workshop, they showed a picture that the first day the Navy kind of came in and told, there's a 3 or 4 day workshop in Reston, Virginia, and the Navy came in and showed this picture of the Patrick Henry, which was about to be decommissioned at the time, and it showed all the cutouts they had made during its 20 or 25 year life, and it looked like a patchwork quilt. Okay, I mean they cut out hull sections to put in to replace this piece of equipment and stuff, and so I went off with the metals guys to talk about titanium, and we were kind of, we were going to be, basically everyone already decided we were dinosaurs thinking about metals. And then the composites guys, all these aerospace guys who don't really worry about cost and stuff back in the 80s, they went off and first they're going to be talking about 4-inch thick composites, roughly. And their solution to this problem of you have to actually repair the submarine every now and then was they would put a hatch in wherever it was needed. okay? And I said, have any of you ever been inside a submarine? You don't have big wide hallways, you know, but you just kind of put it on a dolly and wheel it out, take it up the freight elevator. You know. I also said, well, you know, if we knew this part was going to break down, we would fix it. So, you know, they didn't understand. I mean, these were theoreticians. So the repair costs, composites are basically not repairable. The X-33 spaceplane, not repairable. I mean, the second one is sitting there and it's basically junk. Okay, it's useless. $50 million, you know, you could probably use it to hold water tank in your backyard or something. But can't use it to hold hydrogen. And it's useless. There's no way to repair it. Well, that's not very good when you start investing a lot of money in something that can't be repaired. So that's another problem, Achilles heel of composites. The cost of things is related. Oh, these are terrible.
Can you take them out of the sleeve?
Yeah. You've got your handouts. Okay. The cost of things is related to their abundance in the earth. Iron is the fourth most abundant element in the world. Why is that? Anybody know? It's the fourth most abundant element because iron has the most stable nucleus in the periodic table. And so in a star, the hydrogen goes to helium, and the other things go, and they all stop at iron. And you don't make any elements heavier than iron in a star until the supernova. When the star blows up, that's when you make your elements heavier than iron. And some astronomers won the Nobel Prize a number of years ago for showing that's where the heavy elements come from. But getting back to how do you select materials in Ashby's approach, Ashby developed these maps. If I need to know of different types of materials, what their modulus versus relative cost is, relative cost per unit volume versus the stiffness modulus, Young's modulus. And here are your woods, here's your brick, stone, and concrete. It turns out you can look at different figures of merit, which is the modulus divided by the cost times divided by the density. And you can go through his book, but on this log-log plot, there are certain slopes here. And it turns out that your cast irons and steels and glasses are up in here, and your woods are down here. If you start looking at this, it's the better off you are, the lower the cost over here, and the higher strength is moving up in this direction. It's clear why you build a house out of wood, or you build it out of steel when you use steel studs, because in terms of their modulus stiffness to cost, they fit on this curve. You're not going to make them out of plastic, which is way down here, which has a real cost disadvantage. Okay, you know, if some of the people in Washington could understand these graphs, we could save ourselves billions of dollars of development costs. We're spending money trying to develop things that are orders of magnitude away from reality in terms of cost. And until they start attacking the real problem, in those cases, cost. Now I can go to other things here, and I could talk about that's strength versus relative cost. You get some similar things. I had some other things in here from Ashby. Strength versus toughness, I thought I had in here. Maybe I don't. In any case, I don't have strength versus toughness here. One of the things that drives cost, particularly for metals, but not just metals, but other things, and these are all in your handouts, is the energy cost to produce something. It takes 300 gigajoules per ton of aluminum. It takes 100 gigajoules per ton of plastic. Copper is 100 and could rise because it's in mining cost, although that's really hasn't come to pass. Steel is 50. Gravel is a tenth. Okay, gravel is a structural material. But I mean, a large fraction of your cost of a material is the energy it takes to produce the material. And so you can look at that. Now, it turns out that if you look at how much materials used, yeah, you can probably see this one. This is not, I don't think this is in your handout necessarily. This comes from an internal General Electric report from the 1960s. by a guy named Jack Westbrook. And it's pounds per annum of the structural material versus dollars per pound on a log-log scale. And you go all the way from stone and gravel. At that time, they were using 10 to the 12th pounds per year in the world of stone and gravel. Cement is around 10 to the 11th. Brick is down here. Wood is over here. Steels are over here, alloy steels. Diamond is a structural material. You're using it for its mechanical properties, right? Is way down here. And it turns out you can plot all your structural materials on a graph like this that has to do with cost. And the interesting thing about this, these other lines are ISO market size. Back then in the 60s, it was $1 million market, 10 million, 100 million, $1 billion market. Well, those numbers are 10 times higher now. In fact, steel today is roughly a $400 billion worldwide market. Maybe not 400 billion, maybe it's only 300 billion now. Prices have been going down. But the point is, this line, or this trend, is got a steeper slope than this. If you analyze it, it turns out if you double, or if you cut the price of a material by a factor of 2, you will probably increase the usage of the material by a factor of 4 in the long run. Not in the short run, because people have to redesign it into structures. But if the cost goes down by a factor of 2, you can expect to double your market, because your use will go up by a factor of 4. Okay? So it works pretty well over lots of orders of magnitude as far as that goes. So cost is one of the primary reasons why we select one material over another. This is sort of a revelation to lots of people who are claiming all kinds of things. For example, there's a guy at Rice University named Smalley. Anybody ever heard of Professor Smalley? Won the Nobel Prize a few years ago for discovering buckyballs, these little carbon spheres, and then carbon nanotubes. And Professor Smalley won the Nobel Prize. He has all kinds of research money down at Rice. I had some friends staying with me, and he's just starting. His son is just starting at Harvard Medical School. He's one of my classmates. His son graduated from Rice University, and they built all kinds of new buildings, wonderful laboratories, all because Professor Smalley, discovered these buckyballs, and then discovered carbon nanotubes. And Professor Smalley has been pointing out to people that carbon nanotubes will have a strength of 3 million psi. Pretty impressive, right? Except we had iron whiskers in the 1950s that had strengths of 2 million psi. And people said, oh, we're going to use them in composites. We're going to make tremendous strength composites. And that's what Smalley's, it's the same thing coming around again, except this time he won the Nobel Prize for going around with all this hype. Well, all they've really discovered is the theoretical strength of the material, and in the other class we'll go over how later next week, how you get something like 2 million pounds of strength in something. If you don't have defects in the material, then that's the strength of the atomic bond. And what he's discovered is carbon-carbon is one of the stronger atomic bonds. Well, we've known that for 80 years, okay? And he's now extrapolated it to carbon nanotubes, so big deal. No one's ever measured it, and in fact, the current price of carbon nanotubes is something like a couple $100 a gram, okay? So not per pound, but per gram. Remember, there's 454 grams in a pound, right? So we're talking expensive material. But there are people in Washington who are just funding this because they say, oh, in 5 or 10 years we're going to have these wonderful structures made out of carbon nanotubes. Well, maybe in some laboratory, and some people will get new buildings at their universities, but don't plan on seeing it in production. People are kind of missing the boat on these things. So, okay, that's enough for today.